The next speaker for this session is MacKenzie Carr, and the name of her talk is Digital Convexity in K-trees.
I think you should be able to see my slides now, right?
Yes.
Yeah, okay, great. So I'll be talking about digital convexity in K-trees. This is some work that I did with Kika Meinhardt at the University of Victoria and Ortrud Allerman at the University of Winnipeg. So I'll start with some definitions. So convexity, which we'll denote by this script C, is a collection of subsets of a finite set V that includes the empty set, includes the entire set, and is closed under taking intersections. And then we can define several different types of convexity on the vertex set of a graph. So there are some that are sort of generalizations of Euclidean convexity, but one that's not defined in terms of paths, like the Euclidean convexity that we're used to, is digital convexity. So a subset of the vertex set of a graph is digitally convex if for every vertex set, or for every vertex in the graph, if the neighborhood of the vertex is contained in the neighborhood of the set, then we must have that the vertex is in the set as well. So another way we can think about this is that every vertex that's not in the set must have a private neighbor with respect to the set. So it either must not be in the neighborhood of the set, or it has a neighbor that's not in the neighborhood of the set. And we'll denote the collection of digitally convex sets in a graph. So that's the digital convexity of the graph G by this script D of G. And we're concerned here with the number of digitally convex sets in a particular graph. So we'll denote that by n sub D of G. So as an example, if we look at this graph here with 6 vertices, we have one digitally convex set that's just the vertex 1 all on its own. So to see that this is a digitally convex set, we look at the vertices that are not in the neighborhood of this set. So in this case, those are the vertices 3 and 5, which I've highlighted here in blue. So those two vertices are the private neighbors of all of the other vertices. So the vertices 2, 4, and 6 have 3 and 5 as private neighbors, and then 3 and 5 are their own private neighbors. So that gives one digitally convex set in this graph. If we add in the vertex 2, then we no longer have a digitally convex set, because if we look at the neighborhood of this set, then every other vertex is in the neighborhood. So 3, 4, 5, and 6 are all neighbors of 1 and 2. So none of them have any private neighbors with respect to the set. So this is not a digitally convex set. And in total, we'll get 14 digitally convex sets in this graph. So remember that we always have the empty set, we always have the entire vertex set, and then we would get 12 others. I'll talk for just a second about the original motivation for this problem. So this problem came from smoothing digital images with black and white pixels. So if we think about this as a digital image, if we wanted to smooth this image, we could find the digitally convex set, the smallest digitally convex set that contains these black pixels. So we would call this the digital convex hull of the black pixels. So in this case, we would just add in all of the pixels in this image that don't have, in this case, a private neighbor would be a white pixel that's not in the neighborhood of the black pixels, where the neighborhood is a pixel immediately above and below and to either side. So we would just add in these pixels that I've highlighted in red, and then we would get a digitally convex set in this image. So this would be a smoothed version of the image. So if we think about all the possible smoothed images that we would have, that's equivalent to looking at the number of distinct digitally convex sets. So it's possible that we smooth 2 different images and we get the same smoothed image. So that would be 2 sets of black pixels that have the same digital convex hull. So that's why we're concerned with counting the number of digitally convex sets. And I'll just mention a property of digitally convex sets that helps us identify and count in a graph. So if we have a digitally convex set S, then we can find a second digitally convex set by taking the entire vertex set of the graph and removing the closed neighborhood of our original digitally convex set. So that will give us a second digitally convex set. And because we can pair them up in this way, we know that every graph is going to have an even number of digitally convex sets. So for example, our original example that we had, we found that 1 was a digitally convex set all on its own. And if we take the entire vertex set and remove the neighborhood of 1, we're going to be left with just the vertices 3 and 5. So those form another digitally convex set in this graph here. So LaFrance, Allerman, and Pressey did some previous work on digitally convex sets in trees. So they found that in a tree of order n, we have at most 2 to the n minus 1 digitally convex sets. And then the lower bound depends on whether n is even or odd. But we have essentially some multiple of 2 to the n over 2, then minus 2 digitally convex sets. So the lower bound is attained by graphs that are called spider stars. So the spider star of order 6 is here on the right. And the upper bound is attained by the star of order n. So again, an example with 6 vertices here on the left. So we can see the upper bound, how that comes into play in these stars by looking at what the digitally convex sets are in this graph. So here, if we take any subset of the leaves in a star, if we leave one out, then that vertex is a private neighbor for itself, and it's also a private neighbor for the vertex in the middle. If we include all of the leaves in our digitally convex set, then our vertex in the middle no longer has a private neighbor, so we have to toss that one in as well. So we can match the digitally convex sets with subsets of these leaves. And then in the spider star, we get a lot fewer digitally convex sets, because if we include either of these neighbors of the leaves in our digitally convex set, we have to include the corresponding leaf as well. Otherwise, it doesn't have a private neighbor. So that is going to significantly reduce the number of digitally convex sets we can have. So some of the work that I did was in generalizing these results to 2 trees as well as to K trees. So I'll just throw the definitions up here. 2 trees we construct very similarly to trees. So with a tree, we start with 2 vertices connected by an edge, and then we add a leaf, and we keep adding leaves. So a leaf is a vertex of degree 1. Now in 2 trees, we start with a 3-clique, so with a triangle. And then we add in a vertex of order 2 each time, or sorry, of degree 2 each time. So we want to add a vertex that's adjacent to 2 pairwise adjacent vertices. So to 2 vertices that are on either end of an edge. And then a K tree, we do the same thing. We start with a K plus 1 clique, and then we add vertices of degree K to build our K tree. So we can look at the upper and lower bounds for 2 trees as well. Here's a couple of examples of 2 trees. So we can see that even 2 trees with the same number of vertices don't necessarily have the same number of digitally convex sets. So the 2 tree on the top has 10 digitally convex sets, where the one on the bottom has only 8, which is why we look at upper and lower bounds rather than the exact number of digitally convex sets for 2 trees of a given order. So if we have a 2 tree of order n, then we can have at most 2 to the n minus 2 digitally convex sets. And this is sharp bound because it's attained by 2 trees that are the join of a K2 and n minus 2 independent vertices, isolated vertices. So there's an example of order 6 here. And similar to what we saw with the stars, we can form the digitally convex sets. Now, instead of using the leaves, we're using vertices of degree 2. So we can take the subsets of these vertices of degree 2. If we leave one out, then that's the private neighbor for itself and for that sort of central K2. If we include all of them, then we just throw in those 2 extra vertices as well. And then we can generalize this to K trees. So if we have a K tree of order n, then we have at most 2 to the n minus k digitally convex sets. And we found that that bound is sharp as well. If we look at the lower bound, then we run into some problems. We were not able to actually prove this, but based on some calculations for smaller two trees, we believe that the lower bound on the number of digitally convex sets is about some multiple of 2 to the n over 3, depending on the order of the graph, mod 3. And if this conjectured lower bound is true, then we have a set of two trees that attain this bound, which we'll call the two spider stars. So these are similar to the spider stars that we saw for just trees. So we start with the K2, and then to build our two spider star, we're going to add a vertex W adjacent to X and Y, a vertex U adjacent to X and W, and then V adjacent to U and W. And then we just keep repeating that until we have the number of vertices that we want in our two tree. So we were only able to prove this lower bound up to, I think, n equals 12. But because these two spider stars have a similar structure to the spider stars, it would make sense that this would be the lower bound, but that's still an open problem. And to help us solve this, we looked at, we sort of reduced the scope a little bit, and we looked at simple clique two trees. So these are similar to two trees, but when we're building our two tree, we start with that 3 clique, our K3. And now when we add a new vertex of degree 2, we're adding it adjacent to a 2 clique, so adjacent to 2 adjacent vertices that we haven't used before, basically. So this 2 tree on the left is a simple clique 2 tree, but the one on the right is not, because we have this this edge sort of in the middle there that's used in 3 different 3 cliques, so that's not a simple clique 2 tree. And then we can look at our bounds from earlier and ask whether these hold in the simple clique 2 trees or whether we can improve them. So for the upper bound, if you think back to the graphs that had the 2 trees that had the largest number of digitally convex sets, they were these ones that were the join of a K2 and n-2 isolated vertices. So these are not simple clique 2 trees because we have to keep reusing that sort of central K2 to build these graphs. So we can actually improve this upper bound. So if we restrict to simple clique 2 trees, now the number of digitally convex sets can be at most 2 times the n-1 Fibonacci number. And so this is attained by the simple clique 2 tree that's the join of a K1 and a path with n-1 vertices. So this is the example for n equals 5. And one tool that we used to prove this was the 3-line graph. So the 3-line graph of a graph, we take the cliques of size 3 in our original graph. Those are the vertices in our 3-line graph. And then we join 2 vertices by an edge if their corresponding cliques in our original graph share a common edge. So for example, if we look at our 2 trees from a couple slides ago, in red here are the 3-line graphs. So you can see our simple clique 2 tree, the one on the left, has a path as its 3-line graph. And for simple clique 2 trees, we're always going to get a tree. Whereas because we have those 3 triangles that share one edge in the 2 tree on the right, we're going to get this K3 in our 3-line graph. And so we thought maybe restricting to simple clique 2 trees would help us prove our conjectured lower bound from a few slides ago, but we ended up having to restrict it even further. So we looked instead at 2 path graphs. So these are 2 trees that have exactly 2 vertices of degree 2. So there's an example there on the left, whereas the graph on the right has 3 vertices of degree 2, so it's not a 2-path graph, even though it is a simple clique 2 tree. So we're restricting the simple clique 2 trees even more now to 2-path graphs. And so now we know that their 3 line graphs are paths. And so then when we restrict down that far, then we're able to prove that our lower bound on the number of digitally convex sets. So it's approximately some number times 2 to the n over 3. And the reason we had to do that is because if we look at the vertices in our 2 path graphs that correspond to the end of a 3 line graph, so the 3 line graph here is in red, and then our 2 path graph is in gray, kind of underneath, we only have 2 possibilities for sort of the structure around those vertices of degree 2. So we either have, on the left, we have a vertex of degree 2 that's adjacent to a vertex of degree 3 and a vertex of degree 4. And then in the graph on the right, we have a vertex of degree 3 kind of there in the middle, adjacent to a vertex of degree 2 and another vertex of degree 3. So if we have just those 2 cases, then we found that we can kind of pull off those 3 vertices, look at the digitally convex sets in the remaining 2 path graph, and then see what happens when we add them back on. And then by using induction, we were able to prove this lower bound. The problem is that this bound for 2 paths is not sharp. So if you look at every 2 path graph of order 9, then the smallest number of digitally convex sets is 22, whereas this bound shows us that we have at least 20. So this can be improved for 2 paths, and it can possibly also be improved for simple clique 2 trees. But that is still something that we haven't been able to prove yet. So I'll stop there. Thank you for listening.
Thank you so much, MacKenzie. So we're going to open time for questions. Does anyone have any questions? You sort of mentioned a little bit about the motivation. Could you tell more about it, how this research is related to those?
Yeah, so I'll go back up to, so the original motivation was in digital image processing. So sort of, I guess a big thing is like storing digital images and smoothing them to store it with sort of a smaller amount of information needed. So digital convexity is one way to sort of smooth the image. So if we take this black and white image here, we can smooth the image by finding the smallest digitally convex set that contains these black pixels. But then the problem is if you smooth 2 different images, they might have the same convex hull. So we might get the same smoothed image. So then the question is, like, how many different smoothed images can we have for a given number of pixels? So for a given image size. So I guess the most direct like graph equivalent would be in like grid graphs. So they kind of look like the same sort of digital pixel structure. But then we can generalize that to other graph structures. Does that answer your question?
Yeah. Thank you. Does anyone else have any questions to MacKenzie? Well, then, sorry, did you want to ask?
Yeah, but I'll take it offline since.
Wait, sorry, did you say you wanted to ask a question?
Sorry, no, I'll take it offline since we're running out of time.
Okay. Yeah, thank you so much. Let's give another round of applause to MacKenzie. I appreciate you guys coming in today.
Thanks.
Thank you.